This is the second video in section 2.4 on projections. So I'm going to discuss, really just discuss Theorem 55 and its proof. Recall what the projection is. The projection of W onto V, we calculate it this way. So we have, this is our scalar, and this is our vector V. And now let's just consider another vector. Let's look at W minus the projection. So let's consider this vector here, and we'll see what the properties it might have. First of all, we want to notice that this is actually orthogonal to V. How do we do that? Well, let's take the dot product with V. Remember, dot product distributes over vector addition, so we can distribute our dot product here. When we take the dot product, though, so of V with this V right here, that gives us the magnitude of V squared. So the magnitude of V squares cancel. We have the dot product of V with W minus the dot product of V with W, which is 0. This algebra is given in more detail in the notes. So see the notes for a little bit more detail here, but the dot product of these two vectors is 0, so the two vectors are orthogonal. This is, the projection is just some number, scalar multiple of V, so it's parallel to V. So the projection is parallel to V. This thing here, which is sometimes called the orthogonal complement, so this is orthogonal to V, and the sum, this vector plus this one, is equal to W simply by design. We made it by subtracting the projection from W, so this vector plus the projection is going to be W. Turns out that these are the only two vectors that have this property. So if you take any two vectors whose sum is W, the first vector is parallel to V, and the second vector is perpendicular to V, then these are your two vectors. In other words, the projection and W minus the projection have to be those two vectors. The uniqueness argument is given in the notes. Finally, to finish this section, let's look at example 56. Now, we're going to calculate the work accomplished in pulling a wagon. Recall, possibly from Calc 1, that work is force times distance. And that was fine when we were moving something along a straight line and we had a constant force. And I know in Calc sometimes we changed the force and made a force function and we integrated. But the idea, though, is that that force was being applied in a straight line, either left to right or up and down, generally in Calc 1. But here, we're applying a force at an angle of pi over 3 radians, and that's how we're pulling the wagon. So we're pulling it from a handle. And so what we want to do is we want to find our force vector. So here's a picture of our force vector, and our angle is pi over 3. We're given the magnitude is 10 because 10 pounds of force is being exerted on the handle. That's where the 10 comes from the problem. So let's look at a right triangle whose hypotenuse is 10, and this angle here, this corresponding angle, is pi over 3 radians. Well, now it's just a matter of using right triangle trigonometry to solve the triangle. This is pi over 3, so this is pi over 6, so we know that we have a 1 square root of 3, 2 right triangle here. And our scalar is 5. So I said we have a 1 square root of 3, 2 right triangle, multiply all of those numbers by 5. So we solve this triangle. By solving this triangle, we've now found the force vector. The force vector is 5i plus 5 square root of 3j. So here's our 5i, our 5 square root of 3j. And we can write it in component form this way. It'll make it easier to calculate the dot product. What's our displacement vector? Well, we pulled it 100 feet. And so the displacement vector is 100i, or writing it in component form, we just have the vector 100 is 0. And so from Calc 1, work was force multiplied with distance. Now, work is the dot product of the force vector with the displacement vector. and the dot product of these two vectors is 500, so the work is 500 foot-pounds.